All right, section 6.2, trig functions of real numbers. Okay, there is a nice number file video, and I'll just put the URL here, and if you want to see some nice animations introducing you to the trig functions via the unit circle, I highly recommend this. Okay, so here comes the definition of trigonometric functions in terms of the unit circle. Okay, so the input to our trig function now is going to be a number t that we are not necessarily thinking of as an angle. It's just some number t. And what we're going to do is let p be the terminal point for that number t. And that's what we talked about last time. This is the point on the unit circle that we arrive at when we travel a distance t starting from 1, 0. So that's the terminal point for t, that's the first thing. And then we're going to define the trig functions in terms of this terminal point. Okay, so remember I kind of made this joke, the starting most important trig functions, cosine, sine, and tangent. So here are the starters. So the cosine is going to be the x-coordinate of the terminal point. The sine will be the y-coordinate of the terminal point. And the tangent, well, we can do it either way. We can say that it'll be the y divided by the x, or if we like, we can just say it'll be sine of t divided by cosine t. Okay, the second string trig functions here, secant, cosecant, cotangent. Again, we could define them in terms of the x and y here. We could say that secant is 1 over the x, a coordinate of the terminal point. But I think it's better just to go ahead and define them in terms of cosine, sine, and tangent this way. Okay, so this same memory aid that I've shown you several times now, except this time in the context of the unit circle, the sine function is the y-coordinate of the terminal point, and the cosine function is the x-coordinate of the terminal point. So last time I showed you this, I simply put in the y and the x coordinates, but now we're putting in the sine and the cosine, right? Because that's our new definition for sine and cosine. They are the y and x coordinates of the terminal point. Okay, so again, thinking about the steepness I think is helpful. If we have pi over 6 as the value of t, again, I'm not supposed to think of it as an angle, but it's hard not to. Pi over 6, if we travel that distance, we wind up at a fairly shallow angle. That should have a large x-coordinate, and the x-coordinate is the cosine. Maybe I should have these columns reversed. I might do that. Okay, so just run a few examples, again stressing the fact that in calculus you are going to be expected to be able to do this, so try to practice. So pi over 6, we call this shallow. We're asked for the sine, that's the y-coordinate. A shallow angle should have a small y-coordinate, so this is a half. Okay. Pi over 3, that's a steep angle. Cosine will be the x-coordinate. So a steep angle should have a small x-coordinate, so the cosine of pi over 3 is a half. Pi over 4, this is the medium. That definition for tan is that it should be y over x. And at the medium angle, the y and x's are the same, so that should be a 1. Pi over 2, this is vertical. We want the we want the y coordinate, so we are straight up. That's the point 0, 1. The y coordinate there is 1. Cosine of 0, that's the horizontal. We want the cosine. The cosine will be the x coordinate, and when we're horizontal on the unit circle, we're at 1, 0. So the value here should be a 1. Wow, halves and ones. Okay, so again, try to practice those. So the evaluation of the trig functions in the first quadrant we do by this memory trick, this just trying to memorize those values. And for other values of t, we're going to use the reference number. Okay, so the 3 steps here is given the value of t, we're going to get its reference number, and then we're going to figure out what the correct sign, that's the plus minus, should be for our trig function. And we can do that either by just figuring out what quadrant the terminal point is in, or by using the little mnemonic about all students take calculus. And then we're going to find the value. It'll be the same value for the number t as for the reference, except possibly adjusting the plus minus value. Okay, so we sort of did this before when we were finding the terminal points for, say, 5 pi over 6. We found the terminal point for pi over 6 and then adjusted it. But this time, we don't need both coordinates of the terminal point. We only need one of the coordinates. All right, so let's try A. We want the cosine of 5 pi over 6. So the reference number is pi over 6. We're asked for the cosine, and that's the x-coordinate. It's hard not to do actually think about the terminal point. Okay, so this is a shallow angle, so the cosine pi over 6 is root 3 over 2. But adjust sign, sing. Right, the number 5 pi over 6 should be negative. The number 5 pi over 6 is in quadrant 2, and so the x-coordinate is negative there. So we have to adjust the sign. So this should be negative root 3 over 2. Oh. Try one more. Oh, there. Okay, try another one here. B. So we're asked for the, I better put this because it might scroll off screen here. We want the sine of 7 pi over 4. Reference numbers, pi over 4. So we compute from memory the sine of pi over 4. Let's see, that's the medium. So that should, the medium angle, so this should be a medium value, root 2 over 2. And now we adjust sign. Okay, so 7 pi over 4, this distance has put us down into Q4, and the y coordinates are negative down there, so we need to negate this. All right, last one. Let's see. Oh, yeah, so it is off screen. We want the tangent of this angle. Not angle, this number. The tangent of minus 2 pi over 3. That looks funny. So what we're asked for, the reference number here is pi over 3. So what we're going to compute, sorry, my typesetting is getting out of hand. All right, this is the steep number. So it should have a large y coordinate and a small x coordinate. So this is root 3. Adjust sine 4. So go back to the picture again. We're down in 1 to Q3, and both the x and y are negative in Q3. So since both are negative, the ratio will be positive. So there is no negative to add on there. Okay, so if you think about the actual x and y, and whether x and y are positive or negative in each quadrant, you can decide on how to adjust the sign, the plus minus. But you can also fall back on this technique as well. All students take calculus. In this third quadrant, tangents were positive. So that's why, a separate reason why you know not to negate this value here. Okay. Oh, more examples. Yeah, so... yeah, I'm not sure that we need to do all these additional examples. Yeah, I think I will skip those additional examples. All right, so we are at about 12 minutes now. Actually, I'll put these additional examples in the notes. Maybe you can pause and go to the notes to check your answer. And pause, work them yourself, and then go to the notes to check. Okay, so what we're going to look at now is taking trig of a number versus trig of the opposite of that number. So in our current context, remember the sine of t, say, is the y coordinate that you wind up at, y coordinate of the point you wind up at if you travel a distance of t. If instead we take sine, say, of negative t, we're going to travel the same distance but in the opposite direction. We'll be going clockwise. So by the symmetry of the picture here, if we go the opposite direction, we'll wind up at a point that has opposite y coordinate. The x coordinates will wind up being identical. So if we travel t or minus t, x's are the same, but the y's are going to be opposite. Okay, so if we travel a distance t, sine will be y, but if we look at sine of negative t, this will be a negative y. So sine of t and sine of negative t are opposites. However, if we look at cosine, if we travel the positive distance t, we wind up at a terminal point with coordinate x, and we'll get the exact same x coordinate on our terminal point if we go minus t. Okay, so for tangent, we wind up at we wind up at the point xy, so the tangent is y over x, and for tangent of negative t, our terminal point is negative y over x, and so tangent of negative t has this formula. Okay, so what we see is that sine of t and sine of minus t are opposites. Cosine of t and cosine of minus t are the same, and tangent t and tangent, these are opposites as well. Okay, so here's a vocab refresher here. A function with this property where f of minus x is exactly the same as f of x, that's called an even function. And if f of minus x is the opposite of f of x, that's called an odd function. Okay, so here's the name calling. Cosine of t is an even function. That's because cosine of t and cosine of minus t were exactly the same. Sine and tangent were odd functions. All right? Maybe I'll go ahead and put the formulas in. This is since cosine of minus t was exactly the same as cosine of t, and sine of minus t was the opposite of sine of t. I'll run on here. And we also saw that tangent of minus t was the opposite of tan t. Okay. So it's useful to put these, I don't know, I would call them identities. I'm not sure our book calls them identities, but if you can remember these odd and even properties, this sometimes helps and allows you to skip over working with reference numbers. So, for example, if we want to compute cosine of pi over 3, okay, well, negative pi over 3. Well, if you remember that cosine is an even function, that tells you that cosine of negative pi over 3 should be exactly the same as cosine of pi over 3. Okay, so pi over 3, that's a steep angle. We want the x-coordinate. The x-coordinate should be the small number. Okay, so if, like I say, if you remember this even property for cosine, you get to skip past thinking about the reference numbers as a separate thing. Oh, I guess one more. So find tangent of negative pi over 4. Okay, so if you just remember that tangent is an odd function, this will tell you immediately that this is the negative of tan pi over 4. Okay, so this should be negative 1. Okay. So we're going to look at these identities that we've seen once before, and they have not changed. These are the potential definitions for cosecant, secant, and cotan, and tan and cotan. I would more likely just say that these are the definitions rather than saying that they're identities. And then the Pythagorean identities, we showed these before. They relied on the Pythagorean theorem. Technically, the proofs now rely on the fact that we are working on the unit circle. So the proof that sine squared t plus cosine squared t should equal 1 relies on the fact that the terminal point for t is cosine t sine t, and the fact that that terminal point is on the unit circle means that when we plug in to the equation x squared plus y squared, we will get equality. Okay. Yeah, so the identities have not changed, and we're going to use them in the same fashion that we used them before. We'll express one trig function in terms of another trig function. So here's a specific example with numerical values. So cosine t is 3/5. We don't think about drawing an angle this time. Instead, we just solve the identity. We get cosine t equals this. Sorry, we solve for sine. Sine of t is equal to the square root of 1 minus cosine of t squared. Gotta get my square in here. And this is plus minus. So sine of t will be equal to plus or minus the square root of 1 minus, for the specific example that we're looking at, minus 3/5 squared. And maybe I should do this in more steps. This is going to be a familiar 3, 4, 5 triangle, so that should be 4/5 there. But we're told that t is in Q4. Actually, it's wrong to say that t is in Q4. We should say it has terminal point in Q4. Sign is negative down there. So the sine should be negative 4/5. Oops, I missed my equal sign. And for the tangent of t, we don't have to do anything more than just use the fact that it's sine over cosine. So the cosine was 3/5. That's the one that we were given. We just computed that the sine is negative 4/5. So this will simplify down to negative 3/4. Okay, so yeah, a numerical example, and then here's one where we're going to do a symbolic example. So again, expressing one thing in terms of another. To express tangent means we need tangent equal to some formula on the right-hand side that only has sine in it. Okay, so this will be sine t, and downstairs we're going to have to replace the cosine with square root 1 minus sine squared t. Okay, as we do that, we need the plus and minus possibility down here, and now we just have to worry about making the correct choice. So if we're in quadrant 3, we want the tangent to be positive. All students, yep, the tangent needs to be positive, and the sine down in quadrant 3 is negative, so in order to get a positive, we'll need a negative over a negative. I better write out a little bit of that. In Q3, tangent is negative. Is positive. And sine is negative. So we choose negative square root downstairs. So that negative over negative gives the positive we need. Okay. All right, could put in another timestamp, but let's just finish it off here. So it is a strange evolution of the definition for our trig functions. And just to talk about just the sine function, to walk you through where we've been with this. Initially, the sine function was defined just for right triangles, and we defined it for the acute angle in a right triangle as being opposite over hypotenuse. That was the SO of SOHCAHTOA. Okay. Our next step, we extended this idea to angles that went beyond 90 degrees. We put the angle in what was called standard position, and then defined the sine as being the y coordinate of this point divided by the distance r. And that definition allowed us to extend values of sine for angles that went beyond 90 degrees. Right? We still wind up calling sine equal this y coordinate divided by this distance r. Where we are now is that there is no angle. Right? This t is not thought of as an angle. Instead, it's thought of as a distance that we move along the unit circle. And that distance brings us to a terminal point. And now sine of t, I had it written up above, is the y coordinate of the terminal point. Okay, so why do we do this? Why are we doing so many different takes on the sine function? Well, in many contexts, we want to be computing trig functions, sine, cosine, whatever, in the context where the input is not an angle. And so that's the perspective that we want to have for this chapter. The t will not necessarily be corresponding to any particular angle. It will just be some input number.